Welcome to this video. My name is Mark Sadian. The date today is August 6th, 2024. This video is going to focus on horizontal water flow, velocity, and range. It's a hydrodynamics problem. So there's several problems to solve, but the first one is what is the discharge velocity of the water flow. So the first solution is to use the free fall equation, the delta D on the y-axis vertically. So if the water wasn't moving and we just dropped it from a static point, it would obey the gravitational drop of what amounts to correlating to projectile motion. So we can take the 4.5 feet altitude and convert it to meters, and then simply take the gravitational acceleration on Earth, 9.81 meters per second squared times t squared, and then just simply solve for t squared. So it would take 0.53 seconds for the water to free fall if it wasn't moving. So then we can describe velocity, which is distance or range in this case, divided into time, which in this case is the free fall. So we'll convert the range to meters. So we have 2.75 meters per second velocity of the water, converting it back to feet per second. So 9.02 feet per second, or 2.75 meters per second. So the second problem is what is the water's input velocity. So the easiest way is to use the continuity equation. So we take the cross-sectional area on the input side, which is 0.5 square feet. We don't know the input velocity. Then we just solve for the output cross-sectional area. So that's a taper ratio of 1 to 0.33. So 0.8 times 0.33 is the diameter of the output. So we divide it by 2 to get the radius squared times pi. Then we record that value, and then we know the output velocity is 9.02 feet per second. Because it's feet per second, or because it's square feet over square feet, they cancel out, become a ratio. So we calculate 1 foot per second as the water's input velocity through the duct. Next is what input water pressure, PSIG, is required. And this is dynamic pressure, by the way, so, because it's moving. So we could take the pressure ratio, which is the ratio of the cross-sectional areas at the input to the output. So again, we would solve for the ratio of the cross-sectional area. So it should be somewhere around 9, but to be exact, it's 9.09 to 1. So next, the relationship between pressure and velocity is the P is equal to 1/2 rho V squared. So the rho is the density of the water. So we got to use the metric system. Here is 1,000 kilograms per cubic meter, and we know the input velocity in meters per second is 0.3 meters per second. So after substituting, we compute 45 pascals, 6894.75 pascals per psi, and note that's a pretty large input diameter, so it's not going to require a whole lot of pressure, although the power to overcome the pressure ratio, that's a different aspect, but the input pressure is 0.0065 psi. Uh, 0.0065 psi-G dynamic. So output water pressure psi-G dynamic is required, and again, we can just multiply this times the pressure ratio, so it's 0.06 psi-G dynamic. So next, what is the pounds per second and gallons per minute water flow? And that's US gallons liquid, or 3.78 liters is 1 US liquid gallon. So simply all we need to do is take the cross-sectional area of the output of the nozzle, so that's the 0.8 input times the taper ratio, so it's obviously less than the input, divided by 2 to get the radius of the output nozzle, squared times pi. So this satisfies the two-dimensional metric. Then when we multiply it times the velocity through the output nozzle, that's the third dimension. So when we multiply these out, we get the three-dimensional cubic feet per second flow times the US value for water density, which is 62.4 pounds per cubic foot. This ends up becoming 30.9 pounds per second. And if we multiply that times 60 seconds, that's 1854 pounds per minute water flow. And then we know 8.3 pounds to a US gallon, so 223.4 GPM. So lastly, we have how much horsepower it will actually require to push that water through the input larger diameter, through the 5-foot duct and out the nozzle. So we have to define what a horsepower is. This is 550 foot-pounds per second, which is equal to 746 watts. So if we were to divide these two values, 550 over 746, this translates to 0.737 foot-pounds per second. Mechanical power is equal to 1 watt. So if we take just the average water velocity through the duct, it's simply just the output velocity of 9 feet per second plus the input velocity of 1 foot per second divided by 2. So we get 5 feet per second average water flow through duct. So if we were to take the 30.9 pounds per second times 5 feet, this would translate to, over 1 second, 154.5 foot-pounds per second. Then if we divide that into 0.737, we get 209.6 watts divided into 746. So it's 0.3 horsepower without the pressure ratio. So if that was just a straight duct without a taper, it would be a 0.3 horsepower, not including the hydraulic pump efficiency loss, but because we have a pressure ratio of 9.09, we must overcome that, so ends up becoming 2.73 horsepower. And then your average hydraulic pump has 85% efficiency, hydraulic efficiency to the pump. So if we find the inverse or the reciprocal of that value and multiply times 2.73, this becomes 3.2 brake horsepower is required to drive the hydraulic pump. So 3.2 brake horsepower from the motor or engine driving the hydraulic pump would be required to then push water through this 5-foot duct with a taper ratio of 1 to 0.33, input diameter 0.8 feet, and output diameter is the product of 0.8 times 0.33. This would result in the 9.0 feet per second output velocity, yielding a 4-foot range if the duct is 4.5 feet above ground, and then the input velocity of 1 foot per second, 0.0065 psig, dynamic pressure on the input side, 0.06 psig dynamic on the output side, and 30.9 pounds per second mass water flow, or 223.4 gallons per minute. And so whatever hydraulic pump is driving that water, its drive motor or engine would have to be rated at a 3.2 brake horsepower output, which again is only 1/3 if it's of the total input power if it's a gasoline engine, and it would be electric motor, it'd be somewhere around, if it's brushless, around DC brushless, if it was driven by DC brushless motor, then 0.8, 1 over 0.8 times 3.2 brake horsepower, and if it's a AC motor, then 0.8, 1 over 0.85. But whatever motor is driving that hydraulic pump, it have to have an output, or we'd say a drive horsepower into the hydraulic pump of 3.2 brake horsepower. Thank you for watching this video and have a great day.